Hello everyone. My today's presentation is on multi-seismic attribute and petrophysical studies for a low temperature geothermal field in the Netherlands. And I am Sumit Verma and I work at UT Permanent Basin as an assistant professor, and in this study I have my co-authors Shuvajit Bhattacharya, who works at UT Austin, and Carolina Mejia, who is at UT Permanent Basin. So let's start with the basics about geothermal energy. So geothermal energy is the heat derived within the subsurface of the earth, and the temperature, as you go deeper into the subsurface, it increases, and the temperature gradient in general is around 20 to 25 Celsius per kilometer. And at these kind of gradients, we can see the temperature in the common depths of exploration around, say, 40 degrees to 75 degrees, and such geothermal energy can be utilized for say direct use. Also it can be utilized for heating purpose, say district heating, or greenhouse gas, or say greenhouse farming heating. So further, if the temperatures are higher or the temperature gradients are more, we can reach to a place where the temperatures can be, say, 175 degrees or more. There, the conventional geothermal can be utilized for power generation, where the steam generated from geothermal is running a turbine, and then that generates electricity. So in general though, in oil fields we have low to moderate temperatures, and with a common like general temperature gradients. So we can utilize this for low temperature geothermal and utilize it for heating purpose. In Netherlands, the temperature gradient is around say 31 degree Celsius per kilometer, and with this kind of temperature, they have most of the geothermal energy for commercial greenhouse horticulture being utilized. So in Netherlands, as per statistics, 11% of the total energy comes from renewable, and that was in year 2020. The year before it was around 8.8%. So there has been a steady increase in the contribution from renewable energy. And also this renewable energy includes the geothermal, which has been increasing since the last 10 years. So in from 2011 to now, the annual average growth for the geothermal energy has been say 52% for Netherlands, which is quite high compared to the other neighboring countries or European nations. So here this is because they are releasing a number of permits for geothermal exploration. Here this map of Netherlands shows the geothermal permit areas, and our study areas lies here in the northern part, close to MN area. And coming to our field, the field lies here. This is MN here, and this is the outline of the seismic survey area. And the choosing this seismic survey or this study area was because we had the data availability which we require for geothermal exploration or evaluation. So here we have this area in the Schönebeck oil field, that is a part of say Lower Saxony Basin. It's on the western margin of it, and in this area in 2020 De Groot et al. Studied say for geothermal, and they suggested that at the depths of 1500 meters, with the temperature of 61 Celsius, this can be utilized for geothermal exploration. as geothermal, such low temperature geothermals are very common. It can be a big success for heating up the districts and all, and such heat can be utilized for, say, commercial greenhouse farms heating. And in Netherlands, the most common system that is utilized there is called a doublet geothermal system, in which they have one producer well where they produce the geothermal fluid from the geothermal reservoir, and then when it comes to the surface, it goes to a heat exchanger which extracts the heat from this fluid, and then the injector well pumps it back inside the reservoir. And the average distance, or say on an average, the maximum distance here is around 1.5 kilometers, which is around a mile. And in our study area, or in our study, we performed a preliminary subsurface characterization of our data sets to find, say, fault with the help of seismic attributes. Why we study faults? Because faults influence the heat flow and permeability. And also fault reactivation can cause induced seismicity. So it's quite important to understand fault characterization. And petrophysical analysis was also performed for understanding the porosity and permeability, since they influence the flow rate on the wells, and that's also one more important factor for geothermal. So coming to the tectonostratigraphy of the study area, the basin was formed as a result of a Mesozoic crustal extension. You can see several rifting events here, and after these rifting events there is orogeny, and that shows a complex history of the basin, and that shows up in the seismic data. So that's what we find polyphase fault here, and we utilize seismic to study that. So in the current geothermal reservoir and their uses for in Netherlands, we can notice that say most of the wells for geothermal are drilled between, say, 1600 meters to 2500 meters, and they land mostly in, say, Upper Jurassic, Lower Cretaceous formation that includes this Rhineland formation. And our target formation is here is actually Bentheim sandstone, and also the Triassic sandstone. So further, the most of the energy produced through geothermal that is used for heating, and that is mostly, say, greenhouse heating, and there is no energy actually, geothermal energy, that is utilized in Netherlands for power generation in general. So with that, let's move to the regional temperature maps and at depth. So here you can see with different depths the temperature in the subsurface increases, and this is our study area, and here you can see that the temperature is around 50 degrees Celsius, and overall it's from, say, 35 to 60 degree for 1 kilometer depth. And for the 2 kilometer in our study area, we can see the temperatures are between, say, 75 degrees to 85 degrees Celsius, and then deeper you go, you will have a higher temperature. And the higher temperature in this area, our study area, is due to fault salts and igneous intrusions. So this is a cross-section of Netherlands profile showing you different formations from in depth here, and also the temperatures. So let's look at this area, since this is our study area and this is very close to our study area. So you can see this is the Rhineland formation here, and the temperature is around, say, 70 degrees Celsius, and then deeper you go, you will see higher temperatures in the Triassic sandstones. Further, this is our seismic cross section. So this is from south to north here, And you can see a lot of faults here with the broken reflector and some syncline and anticlines here. So let's put our interpretation here. You can see that there are these late Permian strata deposited, which is composed of salts and carbonates, and then above that the formations here are mostly clastics. And then you will see our formation of interest, lower Cretaceous, that's also sandstones and Rhineland formation. And you can also notice here that there are these normal faults, and that's created due to the rifting and the extension. And you might also notice that for this formation, some of the faults are just ending up to this point, and then they are not inside this formation. But since this is a polyphase faulting case, we would like to show you a case study here from North Slope, Alaska. You can see that there's this seismic on which we do not see the fault so clearly. It shows as a flexure here in this green box. But then if you zoom into that, you can see small flexures, and then if you analyze seismic attributes, you can see these as very clear faults here on this seismic attribute analysis. So we will utilize that for our study as well. And the surface that we are going to use here will be the top of this lower Cretaceous formation here, the black line. And if we see it in the three-dimensional view, you can see that there is a big anticline here, and there is say a syncline here, one more syncline, and another syncline here, smaller one. And you can also see that there is a fault cutting across this, and then there is a fault cutting also quite perpendicular to this the ridge line. And now if we look at the seismic attributes, so this is a 3D view for coherence and curvature extracted along that surface. So you can see that there are these faults here, and you can also see associated most positive curvature anomaly here. And this is the line that I had shown earlier, and then in this part there were no actually faults. But if you look at that, there are some lineations present here, which might be due to the flexure that is generated because of the some fault which are not seen so clearly on the seismic. So here also we can see that there is this fold and this kind of a ridge, and on which you can see lineations along this direction, along this hinge line of most positive curvature anomaly. And similar most positive curvature anomaly can be seen here and here. So when you look at a reference here, say Chopra and Marford into 2011, they based on the structural geology's view of say faults and how the fractures can form on that. Here you can see that the fractures will be forming along the hinge line, and the curvature K1, which is the most positive curvature, same as this one, will be able to extract it, and the strike of this curvature would be able to give you the direction of that fracture. So let's look at that attribute here. So this is the curvature strike. This is the most positive curvature strike, and that is modulated by the most positive curvature magnitude. So what I'm trying to do here is I'm trying to show you the areas as bright colors where the curvature magnitude is high, and then hide it or make it black where those areas are actually have the lower curvature values. Okay, so here you can see this fault is highlighted here with the yellow color because that's the strike line of that fault here. And you can also notice that if we have to find out similar faults like this, which may be genetically related. We can look for the similar color. So we can see here some of these things are very similar in the orientation, so they might be genetically related. Also, there is another fault here. You can see which has a different orientation, and similar to this, there is another fault that is shown up here. So they might also be related. Further analysis is actually required, but then we can make this kind of comparison here and utilize seismic attribute like this. And also you can see this axis along which the ridge was shown, and you can see the lineations here showing up more clearly, and then the lineation direction is also quite clear. So we can see similar lineations here, here, and here, and they can be associated with some fractures here. And now also the lineations that we are seeing earlier, they are actually also more clear here in this direction. So they can also be associated with some kind of faulting, which is not showing a high throw but very small throw, and shows up just as a small flexure on the seismic. So we can utilize this seismic attribute for finding such faults. Further, coming to the petrophysics, we want to find out more about, say, porosity and permeability. And here our formation of interest is Rhineland sandstone, which is here. You can see this. And when we analyzed it, we found that it is mostly sandstone here, and that has a very high porosity. And with our analysis on the data obtained in this area of porosity and permeability, we can see that there is a strong correlation between porosity and permeability. Increase in porosity has an increase in permeability. So for the shallower formations like Rhineland, there is high porosity and permeability. But the temperature in these reservoirs is lower compared to the ones which are deeper. But in the deeper reservoirs, there is a less porosity and also low permeability. So there is a challenge here, like one of them has one of the good things and the one bad thing, and same as the deeper ones. And so here the flow rate actually changes between, say, 100 to 30,000 barrels per day, and that will also again depend on porosity and permeability. So this is a very wide range of flow rate. So we have to consider all these factors for finding out the most appropriate geothermal reservoir and then the production methodology. So let's come to the conclusions now. So the study area has a potential for low temperature geothermal energy production. Faults, salt, igneous intrusions provide elevated heat flow in our study area. Seismic amplitude, coherence, and curvature attribute delineate polyphase faulting, and there are two sets of faults, and there is a one orientation of fold along which there can be fractures. So this can be analyzed further, and petrophysical analysis indicate excellent porosity and permeability for hot fluid production. And the induced seismicity is a risk as everywhere else, so it must be studied properly. Thanks to the Geological Survey of the Netherlands for making 3D seismic data available, and the AASPI program was used to compute seismic attributes, whereas Petrel from Schlumberger was used for seismic interpretation. And thank you all for listening to my presentation.